Hi. Okay, so as I mentioned last time, we're wrapping up. This is really the last section that we're going to do. So we're starting on the check-in with the obvious thing. We have a matrix and we want to find the eigenvalues and the associated eigenvectors. I used a couple words there that we're actually going to see today, but it's pretty clear what they mean. Okay, so let's have a whack. So let's see. The matrix is let's see. A is, in my notes it says 1 minus 3, 3, and then 3 minus 5, 3, and then 6 minus 6, 4. Okay. Okay, and of course when we want to find the eigenvalues, we want to look at A minus xi. X is a variable, and so we're looking at let's see, that's 1 minus x minus 3, 3, and 3 minus 5 minus x, 3, and 6 minus 6, 6 minus 6, and then 4 minus x. Okay. Now, so when you take the determinant of A minus xi, it's a 3 by 3 determinant, so you could do it in a variety of ways, but one way is that we saw a formula for 3 by 3 determinants, so of course you could use that. That's actually how I did it. I worked it out with the formula for 3 by 3 determinants, and I'll spare you the sort of 10 lines it took me to get it right, and I'll just say that it is minus x cubed, plus 0x squared, plus 12x, and then plus 16. Now, as always is the case with a cubic, it's not, we don't have sort of familiar high school experience from factoring cubics so much, but this is kind of a cooked up problem. So so that is to say, I'm going to look at the divisors of 16, and one of them is the roots. So when you try the divisors of 16, you find that x equals 4. So that's the characteristic polynomial. So that's question 1. And now I find that x equals 4 is a root of the characteristic polynomial. So of course, if it wasn't sort of cooked up to come out to have nice answers, then I'd be in some trouble. I'd have to do something more sophisticated, but that's just beyond the scope of what we're talking about in this course. So it is cooked up, so I got x equals 4. If you factor out x equals 4, if you factor out the x minus 4, then what you get is x minus 4. I did the division, and I got x minus 4 times x squared plus 4x plus 4. And you can either recognize how to factor that, or else you can you could use the quadratic formula. Or you could just eyeball the answer to get a complete of x minus 4, x plus 2, and x plus 2. That is to say, positive 2 is a repeated root. Okay. Okay. So next I need to figure out here what is the what are the eigenvectors, eigenvectors associated with an eigenvalue of 4, and what are the eigenvectors associated with an eigenvalue of minus 2. So I'm going to need a new piece of paper. That's not going to fit all that in that piece of paper. So I've got too many papers here floating around. Let's see. Okay, so for lambda 1 equals 4, so I just simply look at what happens when you plug in 4, 4, 4, and 4, and at the resulting linear system. And so what I get is minus 3b1 minus 3b2 plus 3b3 equals 0. 3b1 minus 9b2 plus 3b3 equals 0, and 6b1 minus 6b2 equals 0. And really, I'm just gonna, oops, sorry about that. Just gonna have a whack here at Gauss's method. I took row 1 plus row 2, and also 2 row 1 plus row 3. And I get here, let's see, minus 3b1 minus 3b2 plus 3b3 equals 0, minus 12b2 plus 6b3 equals 0, minus 12b2 plus 6b3 equals 0. So it's straightforward Gauss's method. Obviously, I'm going to do a minus row 2 plus row 3, and that'll finish me off. So minus 3b1 minus 3b2 plus 3b3 equals 0, minus 12b2 plus 6b3 equals 0. And so I get that what here, b2 is 1/2 of b3. Obviously b3 is free, and so I'm expressing b2 as in terms of b3. And then plug that back into the original equation, into the top equation, minus 3b1 minus 3/2 b3 plus 3b3 equals 0, gives me what here, minus 3b1 plus 3/2 b3 equals 0, and so b1 is 1/2 of b3. Okay, so I decided I was going to do out that calculation just to emphasize that there's nothing happening here that isn't routine Gauss's method stuff. So so what we get then is a collection of eigenvectors. The eigenvectors are the non-zero members. Eigenvectors are the non-zero members of this vector space. It's all the multiples of b3. It's 1/2, 1/2, and 1 times b3, where b3, of course, is a complex number, and that's called the eigenspace. Eigen is a German word, means something like characteristic of. So that's, yeah, and the eigenvectors are the non-zero multiples. So b3 can be any complex number. It could be 5 or 12, but it could also be 3 plus I, 12 minus 4i. And then finally, maybe I'll put a line there, if I look at lambda 2 equals 2. Then I get 3b1 minus 3b2 plus 3b3 equals 0. 3b1 minus 3b2 plus 3b3 equals 0. 6b1 minus 6b2 plus 6b3, sorry about the handwriting, equals 0. And again, where the heck did that come from? Well, I have up here, I have this, and I'm simply plugging in lambda equals minus 2. So I'm simply plugging in here lambda equals minus 2. 1 minus a minus 2, negative 5 minus a minus 2, 4 minus a minus 2. 1 minus a minus 2, negative 5 minus a minus 2, 4 minus a minus 2. All right, and then off we go with Gauss's method. So it's obviously here minus row 1 plus row 2, minus row 1 plus row 2, and minus 2 row 1 plus row 3, minus 2 row 1 plus row 3. I'm sorry, it's a little bit insulting at this point in the semester for me to not just say, you know, well, you get zeros there. But so I told myself I was going to do it out long, and here I am. 3b1 minus 3b2 plus 3b3 equals 0, and of course 0 equals 0 and 0 equals 0. So then I'm looking here at b1 is b2 minus b3. So this is a two-dimensional. Remember that minus 2 was, this doesn't look very good, does it? So equals minus 2. There we go. So remember that this was a repeated root. So it appears twice when you factor out, and we happen to get a two-dimensional subspace, two-dimensional eigenspace. So when all is said and done here, I get v sub minus 2 is the set of all b2 minus b3 and b2 and b1. What? And b3. Couldn't read my own handwriting. Where b2 and b3 are complex numbers, and that is to say, you get it's the set of 1, 1, 0, 1, 1, 0 times b2 plus minus 1, 0, 1 times b3, where b2 and b3 are free. So easy to write reals there, but reals isn't correct. So we get a two-dimensional eigenspace associated here with the repeated root of minus 2. Okay? Okay, so the calculations go like the calculations from last time. All right, very good. So now we're ready to finish off. So very exciting. Okay, so we already saw that you get a polynomial, and that the polynomial can be sometimes awkward to factor, but that nonetheless you get a polynomial. That's called the characteristic polynomial of the square matrix T. The characteristic polynomial of the square matrix T is the determinant of T minus xi, where x is a variable. Characteristic equation is set at equals 0. And of course, the characteristic polynomial of the transformation T is the characteristic polynomial of any matrix representation. So I've already defined the characteristic polynomial of a matrix, so the characteristic polynomial of a transformation I can define as the characteristic polynomial of any matrix representation. Now, the characteristic polynomial of an n by n matrix is of degree n. So the exercise there checks that the characteristic polynomial of transformation is well defined. That is to say, it's the same no matter what basis we use for the representation. But we try in these slides to stay away from it's not a small point, it's an important point, but you got to focus on something. Van Clausewitz says the general who defends everything defends nothing. So too here you got to make some point, and the point we're trying to make in these slides and in these videos is to give some concrete feel to what these things are about. So the lemma is that a linear transformation on a non-trivial vector space has at least one eigenvalue, and the reason is because in the complex numbers, the characteristic equation will have a root. It might have the same root repeated n times. That could happen, so you only have one eigenvalue, but nonetheless, it's got to have at least one. So any root of the characteristic polynomial is an eigenvalue, and in the complex number, any polynomial of degree 1 or greater has a root. And we remark in the last video, remarking again here, that we switched from real number scalars to complex number scalars precisely for this moment, that we want to be able to factor these polynomials, and in order to factor polynomials, in order to be confident that you can factor polynomials, you need to be in the complex numbers. All right, so we always saw that when we found the collection of vectors associated with that eigenvalue, that we got some kind of subspace for the non-zero vectors. So we're calling that the eigenspace of the transformation T. And the eigenspace of a matrix is defined analogously. So you recall that this particular matrix that we saw earlier has three eigenvalues, 5, 4, and 2. And we got the three different eigenspaces. The eigenspace associated with 5, the eigenspace associated with 4, and the eigenspace associated with 2. And again, it's a small point, but I think it's worth noting here that the eigenvectors are the non-zero members of the eigenspace. The eigenvectors are the non-zero members of the eigenspace, and the eigenvectors are the non-zero members of the eigenspace. So the lemma is that an eigenspace has got to be a subspace. I mean, we've done now, I don't know, half dozen examples, and it's been in every one of the examples, so it can't be a surprise, but anyway, it is. If eigenspace is a non-trivial subspace. And the proof is, you have to note that V sub lambda is non-empty. It contains the zero vector for the obvious reason. And then to show that it's a subspace, what you have to do is check closure under linear combinations, and that's easy to see because if you take t and apply it to a combination, then you get in each case the lambdas. So t times zeta 1 all the way down to t of zeta 1 all the way down to t of zeta n gives you lambda times zeta 1, and then the lambdas come out. And so t of the combination is lambda times the combination, and that's exactly the criteria to be in V lambda. Okay, and it contains, the space V lambda contains more than just the zero vector, because by definition lambda is an eigenvalue only if there are non-zero solutions. And then we saw before, oops, I'm sorry, I meant to go back instead of forward, there we go. We saw before that if you have three distinct eigenvalues for this 3×3 matrix, then you got three distinct eigenspaces. We just saw in the lemma that they have to be eigenspaces. So I get a basis. This is a three-dimensional space. Excuse me, this is a 3×3 matrix, and I get three basis vectors. I'll just pick the ones that are laying here. I could take C to be 2, and C to be 5, and C to be -7. Now, there's nothing wrong with that, but I'll just take the ones that are here. This one, and this one, and that would be a basis for three-dimensional space. So what I get here is that for any set of distinct eigenvalues of a map or matrix, a set of associated eigenvectors is linearly independent. The proof is a little awkward. I'm going to actually pass over the proof. It's not ugly or anything, but it's just I'm trying to focus on the computations at the moment. So the proof is done by induction on the number of eigenvalues, and the base step is that there are zero many eigenvalues, and so the set of associated eigenvectors is empty, and so the empty set is technically linearly independent. And for the inductive step here, you can see what you do. You just sort of go up by one. But again, I'm going to pass over that in favor of doing the computations. When a person goes back and looks at the book after watching the videos, you should go back and look at the book. Person goes back and look at the book, you should look closely at that. Okay, so here's the matrix from above with the three eigenvalues 5, 4, and 2. And I just picked a non-zero vector from each eigenspace to get this linearly independent set. So I'm going to do this annoying clicking back and forth. So the 1, 1, 0, there we go. I just picked the 1, 1, 0, just picked it. So that's fine, you can do that. If for some reason it's convenient to do something else, -14, -14, 2, I just picked -7, -7, 1 and doubled it. Not for any great reason, I just did. And then over here with the 1, -1, 1, just to illustrate what kinds of things you can do, I multiplied through by -1/2. So that's all fine, and that's going to be a basis for R3 because it has three elements. This obviously has three columns, so it acts on three tall vectors. Here's an upper triangular matrix. You'll remember that the eigenvalues of an upper triangular matrix are easy to pick out. This upper triangular matrix has eigenvalues 2 and 3. I know that the eigenvalue 2 is repeated twice, but anyway, the eigenvalues are 2 and 3. And you can pick a vector from each of V3 and V2 that we saw earlier, and there you go, you get a linearly independent set. So the criteria for diagonalizability is if you have an n by n matrix with n distinct eigenvalues. If you have an n by n matrix with n distinct eigenvalues, like this guy right here, this is a 3×3 matrix with three distinct eigenvalues. Why then you get a basis of the correct size, beta 1, beta 2, beta 3, by picking a vector from the eigenspace, a vector from the eigenspace for 4, and a vector from the eigenspace for 2. So this is a basis because it has the right size. It's a linearly independent set of size 3 in R3. So it's a basis. And now we saw, of course, it was some time ago now, but nonetheless we saw that if there's a basis that acts in this way, t of beta 1 is 5 times beta 1, t of beta 2 is 4 times beta 2, t of beta 3 is 2 times beta 3, why then you have diagonalizable. So this is our criteria for diagonalizable. An n by n matrix with n distinct eigenvalues is diagonalizable. Okay, now it turns out that distinct eigenvalues, it comes up a lot in practice, and anyway, it gives us a criteria for when is a matrix diagonalizable, and we are interested in diagonalizable, seems like a long time ago now, but we're interested in diagonalizable exactly because we're trying to find representatives of the similarity classes. We're trying to find matrices that represent transformations in somehow the simplest way or a simplest way. And diagonalizable is certainly, diagonal matrices are certainly simple in the sense that, oops, I forgot to slide forward. It's certainly simple in the sense that, that it's very easy to figure out what a diagonal matrix is doing. Okay. So for next time, we're going to talk about the geometry of eigenvectors. The eigenvectors and eigenvalues comes at the end of the course. That always means that a person will be left with some sense of I was busy and I got a little wrapped up. I'm not 100% sure that I understood eigenvalues and eigenvectors. The end of a course tends to do that, and it's also the case that eigenvectors and eigenvalues are maybe not quite as intuitive as some of the other things we do in the course. So I have a little extra section here where we're going to draw a couple pictures. Very good. Okay, so see you next time.